I want to start with the principal axes theorem again, since we're going to look at the quadratic forms geometrically. Let A be a symmetric matrix. Then there's an orthogonal change of variable, x equal py, that'll take the quadratic form x transpose ax into the quadratic form y transpose dy, which will have no cross product term. Okay, so now that diagonal, the orthogonal change of variable comes from the diagonalization of A. So we're going to find P, which is going to be that orthogonal matrix that orthogonally diagonalizes A. And then we're going to look at the columns of P, which will be the principal axes of this quadratic form. Okay, and then the x here is just the coordinate vector relative to those new axes. Okay, back in pre-calculus, you probably studied conics, and you saw that when you had a certain form, x squared over a squared plus y squared over b squared equal to 1, that you had an ellipse. That was the standard form for an ellipse. Okay, so this would be our ellipse in standard form. A hyperbola was one that you could write in the form x squared over a squared minus y squared over b squared equal to 1. So the main difference was that opposite signs of the squared terms. And here's our standard form for our hyperbola. Now, those didn't have the cross product term, the x times y, but you possibly studied some conics that did have that cross product term. When it has that cross product term, there's a rotation of axes that's taken place, so that you still have a conic, but it would be squared up relative to a different coordinate axes. Okay, so if we could find the axes y1 and y2 so that this conic was in standard form, we could get more information about that conic. Okay, so the idea in pre-cal, if you studied rotation of axes, was to determine the angle of rotation, which was this angle right here, rotate the axes so that you could see what the new coordinate axes were, and then you transform the equation so that it removed that cross product term, and you could get an equation that no longer had the cross product term relative to those new axes, the y1, y2. So this conic, you can see by this cross product term, it has that minus 4x1, x2. That conic is a rotated conic. Now, it's not clear by looking at the equation in this form whether it's going to be an ellipse or a hyperbola. But once you rotate it, you'll be able to tell by the standard form. Now, here's a hyperbola that's not in standard position. That cross product term is what tells me that there's a rotation that was involved. So if we looked at if we could rotate it so that we could get the coordinate axes where it was in standard form relative to those, we can get more information about that conic. Okay, so that's what we want to do, is I want to look at one of these conics in this rotated form. I want to eliminate the cross product term by getting that matrix P that's going to contain those axes. Okay, and then we're going to be able to get the standard form for the conic. Okay, so we're going to find those principal axes, which will be the columns of the P. Okay, so here's an ellipse, and the equation is given by this. So this is a quadratic form with that cross product term. So first thing I want to do is to find the matrix of the quadratic form. Okay, so our matrix A, the squared terms, coefficients, go down the main diagonal, and then we split the cross product term in row 1, column 2, and row 2, column 1. So here's our matrix of the quadratic form as it is here with x's. So now I need to find the change of variable, which will be the x equal py, but to do that I've got to find the p, which is the p that's going to, it's the orthogonal matrix that will orthogonally diagonalize A. So let's go over and find the eigenvalues for A. Okay, so we'll get those by finding the determinant of the A minus lambda I matrix. 5 minus lambda, negative 2, negative 2, 5 minus lambda. And that's equal to 0. So I'm going to get the characteristic equation. And so we get eigenvalues of lambda equals 7 and lambda equal to 3. Okay, so we get that x2 is negative x1, x1 is negative x2, and x2 is a free variable. So our eigenvector would be negative 1, 1, corresponding to lambda equals 7. For lambda equals 3, so that means x1 is x2, x2 is free, and so our eigenvector corresponding to lambda equals 3 is 1, 1. So now to form P, okay, we need to find the magnitude of these vectors and normalize those vectors. So P each of these vectors has magnitude 2, square root of 2, so it'll be minus 1 over the square root of 2, 1 over the square root of 2, 1 over the square root of 2, 1 over the square root of 2. Okay, and our diagonal matrix D will have the eigenvalues on the main diagonal. Now, they're going to be what gives us the coefficients of the squared terms once it's been rotated. So our quadratic form, so our change of variables, and that's using x equal to p times y, becomes 7 x1 or y1 squared plus 3 y2 squared. Okay, now I want to point out the columns of P. Those are your axes, okay? So looking at the columns of P, we have negative 1 over the square root of 2, 1 over the square root of 2, which you know those are on the line minus 1, y equal negative 1, negative x. So this would be the vector corresponding to that column 1. Now, I put them in different order. You could have put either vector in either column. I've got them backwards from what they're calling their y1 and y2. So this is the one I'm calling y1 based on my equation. The vector here corresponds to the line y equal to x. So that would be the axis corresponding to that second column of the P matrix. If you recall from pre-cal, or even earlier in this course where we were doing rotations, we had a rotation matrix. It was cosine of an angle, sine of the angle, minus sine of the angle, cosine of the angle. Okay, so I've got my columns backwards from a simple angle. So the angle, if I'd used 45 degrees here, this would have been my y1 here, and this would have been y2, and there would have been 45 degrees. Because I put the columns backwards, the angle is actually going to be, 135 degrees. So I ended up rotating it, or even negative 45. No, not negative 45. So 135 degrees. So our y1 was rotated 135 degrees based on the order that I put my p's in the columns. But you see that this is just a rotation. All we've done is we've rotated all the points from that standard position for that ellipse through that angle. So that you can see that those columns of P match up with a rotation of 45 degrees or 135 degrees. Okay, so that's what a change of one application of a change of variable and what it's doing geometrically.